Dielectric properties. A dielectric is an insulating material in which all the electrons are tightly bound to the nucleus of the atom. There are no free electrons to carry current. That means a bonnet, mica, oil, etc. The electrons are not free to move under the influence of an external electric field. Effect of electric. In the capacitor, the region between the plates, dielectric materials like mica and oil, the capacitance of the air-filled capacitor C is equal to epsilon naught into A by D. That is, the capacitance of the dielectric field capacitor C dash is equal to epsilon naught A by D. Therefore, C dash by C is equal to epsilon R, or C dash is equal to epsilon R into C. Epsilon R greater than 1 for any dielectric material other than air, the capacitor increases is a dielectric placed. Dielectric materials. Introduction to dielectric materials and parameters of dielectric material. Definition of insulating and dielectric material. Dielectric material is the energy gap needed 3 electron volts. An electrical insulating material can be defined as the material that does not allow electric current to pass through it. The dielectric and insulatings are differentiating from their applications. One of the major difference between the dielectric and insulator is that the dielectric stores electric charges while the insulators oppose the flow of electrons. Rubber, glass, oil, diamond and dry wood, etc. Definition of insulating and dielectric material. The arrangement of molecules in the absence of electric field. So whenever electric field is applied, so these molecules will get arranged themselves, that is positive shift in molecules, that is the positive charge will align direction of electric field, the negative charge get aligned opposite direction. Get this is called polarization. The insulating materials, the dielectric properties. Due to the dielectric polarization, the positive charges are displaced towards the field and negative charges shift in the opposite direction, when creates an internal electric field which reduces the overall field when the dielectric itself, the metal plates of the capacitors such as mica, laminated paper, other examples, air, ceramics and etc. The parameters of dielectric material. Static electric field. The electric field is the region of space in which electric charge will experiences a force. The direction of the electric field represents the direction of the force positive test charge would experiences if placed in the electric field. That means the electric field is always positive charges oppose the electrons is a negative direction. So, the electric field charges, the electric field lines of the positive point charges is away from the positive charge and negative charges opposite to the field direction. The positive and negative charges are brought together. The field of interaction between these two unlike charges, force exists between these two attractive nature. That is static electric field, the positively and negatively charged particles brought together, the field of interaction between these two, it form a positive and negative charges of the particles. The static electric field, two positively charged particles, it forming opposite direction of the field directions. The parameters of dielectric material, Coulomb's law, it states that the force between two charges Q1 and Q2 is directly proportional to the product of the charge and inversely proportional to the distance between them. So here Q1, Q2 is the two charges between the distances are, therefore Coulomb's force F is equal to the constant K Q1 Q2 by R square. This is called Coulomb's law. So electric flux, the passing through the plane on the surface, that is called electric flux. Always it passes through the plane surface. The parameter of dielectric material, the electric lines of passes through the plane. The electric flux defined as the number of electric field line passing per unit area. It is represented by psi, and Gauss's law, if the states that the net outward normal electric flux through any closed surface is proportional to the total electric charge enclosed within that closed surface. That means the Gauss's law is electric flux phi is equal to Q Coulomb. The parameters of dielectric material, electric flux density D, the flux per unit area measured at a right angle to the direction of electric flux is known as electric flux density. Then D is equal to psi by A coulombs per meter square, that is equal to Q by A. Electric flux density is also called displacement density. The electric flux intensity E, the electric field intensity at a point is a force experienced by a unit positive charge placed at that point. The field intensity is a vector quantity. So vector means both magnitude and direction. It is denoted by capital E, formula of electric field F by Q. The units is Newton per Coulomb. The relation between electric field intensity and electric flux density, the relation between E and D can be written as D is equal to epsilon E, where epsilon is constant, it is a permittivity constant. Epsilon naught is a permittivity of the free space, epsilon R is permittivity, relative permeability or permittivity. Permittivity, it is the measure of the resistance that is encountered when forming of the electric field in the medium. The relates to the material's ability to transmit or permit the flow of electric field. The characteristics of a dielectric materials are determined by the dielectric constant, and it has no units. Dielectric constant is epsilon R. It is the ratio between permittivity of the medium to the permittivity of free space. Epsilon R is equal to epsilon by epsilon naught. So that is electric dipole, two equal and opposite charges separated by small distance constitute electric dipole. The small distance is small d. One pole is called plus q, another pole is called minus q. That means plus charge and minus charge. Separation of the distance is small d. And dipole moment is the product of charge and distance between the two charges. Therefore, mu is equal to the product of charge and distance. The units is Coulomb meter or debye. 1 debye is equal to 3.36 into 10 power minus 30 coulombs. Polarization. It is a small or slight relative shift of the positive and negative electric charge in opposite direction within an insulator or dielectric or induced by an external electric field. In a simple words, polarization defined as the total number of dipole moment per unit volume of polarized materials. Therefore, P is equal to mu by V, units is Coulomb per meter cube. The degree of polarization depends upon density and dielectric constant of the material. It is found that for many dielectric materials, the polarization vector is raised to electric field E in the dielectric given by P is equal to epsilon naught chi E into E, where chi E is called dielectric susceptibility of electric field. Therefore, epsilon naught is the permittivity free space. E is applied electric field. The polarization P is equal to epsilon naught chi E and E. Dielectric susceptibility chi E, it is the property constant that indicates the degree of polarization of dielectric material in response to an applied electric field. The greater the electric susceptibility, the greater the ability of a material to polarize in response to the field, thereby reduce the total electric field inside the material. The polarizability, when a dielectric material is placed in the dielectric field, displacement of electric charge gives rise to the creation of dipole in a material. The polarization P of a elementary particle is directly proportional to the applied electric field strength E. Therefore, P is proportional to E. P is equal to some constant into E. The constant factor is alpha. Alpha is a polarizability constant. We know the polarizability constant alpha, it is a constant value. Alpha is a polarizability. Clausius-Mosty equation. Clausius-Mosty relation relates the microscopic property polarizability alpha to the microscopic property dielectric constant E. Epsilon r minus 1 by epsilon r plus 2 is equal to n alpha by 3 epsilon naught. Some of the basic definitions. Dielectric constant. The dielectric characteristics of materials are determined by the dielectric constant. The dielectric constant of a medium is defined as the ratio of permittivity of the medium to the permittivity of free space. Epsilon r is equal to epsilon by epsilon naught. The dielectric constant has no units or dimensions. The dielectric constant is also called the relative permittivity of the medium. So, the relative dielectric constant epsilon r is equal to epsilon by epsilon naught. Epsilon naught is permittivity of the medium. Polarization. When a dielectric is placed in an external electric field, the positive and negative charges are displaced from their equilibrium positions by very small distances throughout the volume of the dielectric. The dielectrics are produced. The process of producing electric dipoles which are oriented along the field direction is called polarization of dielectrics. The polarization of dielectric is defined as dipole moment per unit volume. Therefore, P is equal to mu by V, where mu is called dipole moment, and dipole moment is the product of positive and negative charges of separation of the distance. If the number of molecules per unit volume is capital N and each has a moment, then the polarization is given by P bar is equal to the product of N into mu bar, where mu bar is dipole moment per unit volume. And another one is polarizability. When an electric field is applied to solid, electric charges are displaced, causing polarization in it. The induced dipoles of moment mu bar are proportional to the local electric field or internal field EI. Then mu is directly proportional to EI. Mu is equal to alpha into EI, where alpha is a polarizability constant. That means the polarizability constant mu is equal, that is alpha is equal to mu by E. Mu is called dipole moment, E is applied electric field. Therefore, alpha is equal to mu by E. The total polarization of the dielectric material capital N atoms is given by P is equal to capital N into mu, whereas in mu is equal to alpha into EI, the value substitution here P is equal to N into mu, that is equal to N alpha EI. So the polarization is equal to N alpha EI, it is the value. The relation between D, E and P, therefore electric induction E is equal to epsilon naught into E plus P, and D is equal to epsilon into E. Therefore epsilon E is equal to epsilon naught E plus P. Therefore P is equal to epsilon naught epsilon R E minus epsilon naught E. Therefore P is equal to epsilon naught into epsilon R minus 1 into E. That is the relation between P D E relation. So epsilon is equal to epsilon, that is epsilon is a permittivity, is equal to epsilon R into epsilon naught, and simplification finally get at the value of the relation between D, E and P, that is called epsilon naught into epsilon R minus 1 into E, that is the relation of the DE value. Derivation of Clausius-Mosty relation. What is the polarizability? It gives the relation between the dielectric constant of dielectrics and polarizability of the medium. Let us consider the elemental dielectric medium is placed in the electric field. Capital N is number of atoms per unit volume. Therefore, polarization vector is written as P is equal to capital N alpha EI, that is equation 1, and by the relation between D, P, E, the relation is EI, local field EI is equal to E plus P by 3 epsilon naught, that is equation 2. Equation 2, substitute the equation 1, that is EI value substitution the above equation of equation 1. Therefore, P is equal to N into alpha into E plus P by 3 epsilon naught. So that means the value is called P is equal to N alpha into E plus P by 3 epsilon naught. That implies N value B is equal to N alpha E plus N alpha P by 3 epsilon naught. All the P terms is one side, therefore P minus N alpha P by 3 epsilon naught is equal to N alpha E. The P is a common value, therefore P into 1 minus N alpha by 3 epsilon naught is equal to N alpha E. That is, P is equal to N alpha E by 1 minus N alpha by 3 epsilon naught. That means this is one of the equation, that is a polarization vector. And similarly, that implies P is equal to epsilon naught into epsilon r minus 1 into E. The P place substitute the equation, both are the P and P, both are the equal, the equating of two equations. That implies epsilon naught into epsilon r minus 1 into E is equal to N alpha E by 1 minus N alpha by 3 epsilon naught. It can be written as the small changes of the equation that implies 1 minus N alpha by 3 epsilon naught is equal to N alpha E by epsilon naught into epsilon r minus 1. That means N alpha by 3 epsilon naught or epsilon naught into epsilon r minus 1 plus N alpha by 3 epsilon naught is equal to 1. It is a common value of N alpha by 3 epsilon naught, that is N alpha by 3 epsilon naught into N alpha by 3 epsilon naught into 3 by epsilon r minus 1 plus 1 into or is equal to 1, that is N alpha by 3 epsilon naught into 3 plus epsilon r minus 1 by epsilon r minus 1 is equal to 1. That 3 minus 1 it is called plus 2. N alpha by 3 epsilon naught into epsilon r plus 2 by epsilon r minus 1 is equal to 1. That can be written as epsilon r minus 1 by epsilon r plus 2 is equal to N alpha by 3 epsilon naught. This is known as Clausius-Musti relation.
Hi students, in this class we are going to learn about internal field. So first, what is an internal field? or internal electric field. The electric field which is responsible for polarizing a molecule of a dielectric is called internal field, or it is also called molecular field, or also called local field. So, if you take a dielectric material, in the dielectric materials there are made up of dielectrics are made up of atoms and molecules. So, these atoms and molecules not only experience the external electric field, they experience some more electric fields. Those electric fields are produced by induced charges, and also the dipoles inside the dielectric. So, the resultant of the electric field means the total electric field which is responsible to polarize a molecule. So, the sum of all electric fields which are useful to polarizing a molecule of a dielectric is called as a local field, or also called as a internal field. So, this method was derived by using a Lorentz. So, we are deriving the local field by using Lorentz method. In this Lorentz method, we will consider a dielectric material. So, this is a dielectric material, and now this dielectric material is placed between the two capacitor plate. One is a positively charged plate and other is a negatively charged plate. Now, the external electric field direction is from positive to negative. Now not only now we will consider one molecule at the center of the dielectric medium. Now, at a point A, we will consider one molecule at the center of A. At a point A, one molecule is there. Now, how many fields are acting at A for polarizing that molecule which is at a point A? So, one you can observe in the figure. The one is at external electric field, this E1, we can consider this one is a E1, and E1 is the electric field due to charges on the surface of a capacitor plate. And the second one is the E2. E2 is the electric field due to charges on the surface of a dielectric. These are the induced charges. And we will consider one more spherical surface inside the dielectric material. Now, on the spherical surface also some positive and negative charges are induced. Now, the electric field due to these charges is called as a E3 electric field. Now, and one more electric field is acting at A, that is because of the dipoles inside. So, because of these dipoles also one more electric field is acting, that is called E4. So, total 4 number of electric fields are acting on a molecule A, on a molecule which is present at A. So, the resultant of all these electric fields is called as a local field. So, that is EI. EI means internal electric field. EI is sum of E1 plus E2 plus E3 plus E4. So, E1 already we discussed. E1 is the electric field due to charges on the surface of a capacitor plate. And what is E2? E2 is the electric field due to charges on the surface of a induced charges on the surface of a dielectric material, and E3 is the electric field due to charges on the surface of a sphere. E4 is the electric field due to the dipoles inside the spherical surface. So, total 4 electric fields are acting on a molecule. So, here we wrote like where E1 is the electric field due to charges on the surface of a capacitor plate with no dielectric medium. According to Gauss law, we can derive this one as a E1 is equal to rho by rho means surface charge density. Rho is equal to, you can write Q by A. So, E1 is equal to rho by epsilon naught, and what is E2 is the electric field at A due to polarizing charges on the plane surface of a dielectric material. Nothing but, so the expression for E2 is equal to minus rho p. Rho p means surface charge density due to polarizing charges, and negative sign is because this E2 is opposite direction of E1. Now, E3 is the field at A due to polarizing charges on the surface of a spherical cavity. So, now we have to calculate E3. So, to calculate E3, so we will consider that spherical region. What we are considering a spherical region inside the dielectric material. That spherical region here we consider, and this side of the sphere we have positive charges, and this side of sphere we have negative charges, and we are considering a small area ds on that sphere. So, this is the small area ds. This ds area is making angular width d theta at the center, and it is making theta angle with the external field direction. Now, we have to calculate how much electric field for this due to the charge on that surface. So, this we are considering ds area, this ds area contain dq charge. Now, the electric field intensity due to a point charge, the electric field intensity due to a point charge dq is equal to dE is equal to 1 by 4 pi epsilon naught dq by r square. Now, this dE is in the direction of, in this direction, dE is in this direction, which is making theta angle with the horizontal direction. So, now we have to resolve dE into two components. The one is dE cos theta, and another polarization is also making theta angle with the external field direction. So, that is P cos theta. So, the component of the electric field, now the external electric field is in this direction, our electric field is in this direction, means it is making theta angle with the external field. So, this is dE, and now we resolve the dE into two components, and polarization is also making theta angle. So, we resolve dE and P into two components. The one is dE cos theta and the other one is P cos theta. So, now this expression become, now the electric field which is in the direction of external electric field is dE3. dE3 is equal to dE cos theta, we can write. So, we know that dE, substitute dE here. Now, we will get dE3 is equal to 1 by 4 pi epsilon naught dq by r square into cos theta. Now, we have to calculate what is dq. So, according to the definition of polarization, dq is equal to is a product of polarization into area ds, because we know that polarization is equal to dipole moment per unit volume. Dipole moment can be written as one of the charge into distance between two charges. Volume can be written as area into length. So, we can calculate, cancel r and r. You can write polarization is equal to charge per area. So, here it is a dq and area is ds. So, dp is equal to dq by ds. From this, dq is equal to p into ds. Now, I will erase this one. So, polarization, according to the definition of polarization, according to the definition of polarization, dq is equal to polarization into area of that surface. So, polarization, already we know that we divided the by resolving the polarization, we get p value as a p cos theta. So, dq is equal to p cos theta into ds. Now, we saw ds. To calculate the area ds, now here the sphere is like this, and we are considering small area ds. Now, just cut the sphere like this, here we will get A and here we will get P, Q, R. Now, we have to calculate this area. So, the formula for this area is ds is equal to 2 pi into width of radius of that sphere, radius of that spherical part, PQ, and width of that ring, means we are cutting this one. By cutting, you will get like this. It is just like if you cut onion slice, it will just like this. Now, from the center, its radius, here it is P and it is Q and this width is R. So, 2 pi into radius of that part slice and width of the slice is QR. Now, what is a PQ? From the triangle APQ. So, where is A? A is here, APQ. From this triangle, so you can also get here, from the triangle APQ, theta is there. So, sin theta will calculate. Sin theta is equal to, from the triangle, sin theta is equal to opposite side of that one. So, opposite side of the theta is QP by hypotenuse AQ. So, sin theta is equal to PQ by AQ. AQ nothing but radius. AQ are nothing but radius of that sphere, radius of that part, or radius of the sphere. So, from this we will get PQ by R we will get. So, from this we will get PQ is equal to R sin theta. PQ is equal to R sin theta. Now from the sector, it's a sector, from the sector ARQ, we are considering this sector AQR, E sector. From this sector AQR, we know that if you take a sector, it is like this AQR, and here angle is theta. So here the angle is d theta. So d theta is equal to, opposite side of the d theta is QR, QR by a radius of the sector is R. So from this sector dqr is equal to r d theta. So now we derived these two values, one is QR value and other is PQ value. Substitute these two value in ds. So we will get ds is equal to 2 pi into PQ value is r sin theta, and QR value is r d theta. So the value of ds is equal to 2 pi into 2 pi r square sin theta into d theta. So substitute this ds value in dq. Already we know that the value expression for the dq. So this is the dq. So we have to substitute ds value here, and we know the p cos theta here. So substitute dq. So dq is equal to p cos theta into, and ds value is 2 pi r square sin theta into d theta. So now we will substitute this dq value in DE3 equation. Now we will substitute dq value here, dq value we will substitute here. So DE3 value is, DE3 is equal to 1 by 4 pi epsilon naught dq by r square into cos theta. Now substitute this dq value here. So DE3 is equal to 1 by 4 pi epsilon naught, and dq value is P2, you can simplify this one. It says 2 pi p r square sin theta. Already one more cos theta is there. So cos theta is there. So substitute that one. 2 pi r square p cos theta is there. So we will get cos square theta by r square into d theta. Now this is a D3 is the electric field due to small area ds. Now I want to calculate E3 for entire sphere I want to calculate. So for that one, the total electric field which is because of the charges on the surface of a sphere, E3 is integral of dE3. Now you have to integrate from 180 degrees, nothing but 0 to pi we have to integrate. So substitute this dE3 value here, there we will get. So and we can cancel r square here, and pi value here, 2 2s are 4. So simply the constant which is not required for integration is p by 2 epsilon naught into remaining integral is 0 to pi sin theta cos square theta into d theta. Now we have to solve this integration. So by solving the integration, the value of this integration is p by solving this integration we will get 2 by 3. Now substitute value here. So we will get E3 is equal to p by 2 epsilon naught into 2 by 3. So 2 value get cancelled. You will get E3 is equal to p by 3 epsilon naught. So this is the required expression for the electric field E3. E3 is the electric field due to charges on the surface of a sphere. So we calculated E3 here. So next one is E4. E4 is the electric field at A due to dipoles inside the spherical cavity, and all the dipoles inside the spherical cavity, they are oriented in different directions and they are oriented randomly. So because they are oriented randomly, the resultant electric field is 0, nothing but E4 is 0. Now substitute the values of E1, E2, E3 and E4 here. You will get rho by epsilon naught, sigma by epsilon naught minus sigma p by epsilon naught plus p by 3 epsilon naught. So, we will consider this part as a capital E. So, nothing but EI is equal to E plus P by 3 epsilon naught. So, this is the required expression for the local field, or also called Lorentz field.